Okay, I have already drawn a few things on the computer screen for you to look at. One is a review of the actual structure of an electromagnetic wave. It's on the right-hand side here, and you'll remember this from the other day. So we said that light is a form of electromagnetic wave. Electromagnetic waves travel through the electromagnetic field, which is the medium for those waves. And it's not a material medium. It's not made of matter. It was quite elusive for some time. But it is a field that permeates all things everywhere and is basically all around us, like a giant invisible ocean. And only a very small part of it is visible to us. And we said that the waves have an electric part, but at the same time, there's a 90-degree wave, a wave that is perpendicular, that goes with it. You can't have one without the other. So it's a kind of a strange medium, and it vibrates in two different planes at the same time, the electric plane and the magnetic plane. And so every wave actually looks like this picture. The only problem is it's very difficult to draw. So we tend to just draw little transverse waves, and we have to remember in our mind that this is the idea. What's really cool, though, is remember that you can make these waves by wiggling the electric charge or by wiggling magnetism or magnetic waves. Either one produces both waves. So that means that electricity and magnetism are really the same thing. They're just two different sides of the same coin. Okay, and the other picture I have here is a reminder that the different wavelengths or frequencies of light are what make all the difference in how we observe them and how they behave. And so we started off with a picture like this, and I just drew a few representative things. I left out the middle. We started with radio waves at the one end. And we said these were very low energy. Remember that the lower the frequency, or the longer the wavelength, those are both the same thing, right? Low frequency or long wavelength means low energy. And as you progress through the possible levels of energy or the possible wavelengths, we have this range or spectrum, right? And I've drawn some representative waves of each. At the other end of the spectrum, we have the very high frequency, very short cosmic rays, very short wavelengths, and of course these are the highest energy. So down at this end we have high energy. And this is also where you find things like gamma rays would have been the next one over, and X-rays and ultraviolet and so on. And the visible light is sort of in the middle. In my picture we have radio waves, microwaves, infrared, which is heat. And then the next section, sort of in here, was the visible light section. And you should by now sort of have a basic understanding that in that section, the shortest wavelengths, or let's start with the longest on this side, are the red, and then we have orange, which I don't have an orange color, but orange, right, and then continuously shorter, red, orange, yellow, green, shorter still, and blue is the shortest. And there are some numbers we tend to use. We tend to look at the long end of this spectrum, and we see wavelengths around 700 nanometers, a billionth of a meter. So they're very, very short wavelengths in that sense, but they're in the middle of the range where light comes. And then at the other end, we have the blue end, which are shorter. They're about 400-ish in that range, nanometers. So you should kind of have that idea generally in your head. And all of this sort of theory is what's going to allow us to explain what happens when light interacts with matter. What happens when material objects feel these waves? Okay, well the first thing we have to understand is that only charged particles can feel these waves, because it's the electromagnetic field. If you don't have electric charge, you don't feel the waves. It's kind of like things without any mass don't feel gravity. It's the same idea. So, first of all, the interaction of these waves with matter has to involve charged particles. And of course, we have already become familiar with some charged particles. And they are, of course, the proton and the electron. Now, because of the structure of matter, remember that matter is made up of atoms, and in the atom we have a central nucleus where the protons are located along with some neutrons. But that nucleus is very tightly bound together by an incredibly strong force that we really haven't learned much about yet in any of your science classes. But next year you will. The strong nuclear force holds that together. And I guess you could say it basically means that it's not a player in any of the things we observe in terms of light. The other charged particles are the electrons, which are kind of buzzing around or existing around the nucleus in a very sort of odd, wavy particle kind of way. You've learned about the quantum mechanical model and how the electrons are sort of everywhere but nowhere, and the probabilities. But that doesn't all matter for us. All we need to remember is that they're out there, and they're on the outside of the atom. So when things interact with the atom, it's primarily the electrons that are going to feel these waves. So that's the first thing. When light interacts with matter, it is generally interacting with or interfering with the electrons and the kind of motion that the electrons will have. Okay, let's look at that a little bit closer. Let's remember something about electrons. Let me redraw this little picture, or let's draw another one. You're probably taking notes as you go, so we'll draw a model of an atom. Now remember, this is not what atoms physically look like anymore. We've accepted that this is really just a picture that gives us a representation of the levels of energy in an atom. So here's the nucleus, and we won't worry about the protons. But around the nucleus, we have discovered that there are particular levels of energy that electrons can sort of live at. And so we don't mean to imply that they're going around in circles like planets anymore, but these pictures can help us visualize the levels. So it's almost like if you thought about these being like temperatures and you were measuring how hot things were. So the cooler temperatures would be inside tight and the hotter temperatures on the outside. It doesn't mean anything about where they are anymore. But let's look at this. We would have electrons. Some of them would be in the very lower levels of energy. In fact, there would be 2 electrons allowed in this energy level, and they would live there. Then we could have, in the second energy level, some more electrons. This level is actually a little bit more complicated, and it has some sub-levels in between. So you can actually have as many as 8 electrons in this level. 1, 2, 3, 4, 5, 6, 7, 8. And then on the next level, you have an even greater number of possibilities. But we don't need to worry about even that, because we're not worried too much about the chemistry. I'll just draw a couple of electrons on 3 or 4 around the outside for this atom. Okay. What do these energy levels mean? Well, it means that every electron has a certain amount of energy. So you can kind of think of that as, in a sense, that electron's vibration, right, is representative of how much energy it has. So let's see what happens if a wave of red light comes floating in here, streaming towards this atom. Now, a wave of red light has a specific wavelength. We already saw that red light is somewhere around 700 nanometers. Since we know the speed of light is the value c, which is constant, it's 3 times 10 to the 8 meters per second, that never changes, then we can use that with the wave equation, v equals f lambda. Change this to c for the speed of light waves now, and we're not talking about sound waves anymore. We can turn lambdas into frequencies if we wanted to. So we already know a lot about a red light wave. We can also use the frequency and the wavelength to tell us how much energy the light wave has. Now that's not something we're going to actually learn to do. That's next year. But we can accept the fact that a red light wave has a very specific amount of energy associated with its 700 nanometer wavelength. You could think of it like it's a very specific wave. Okay? Now, when this wave hits an atom, it's going to interfere with or interact with electrons. Because electrons are charged particles, they will feel this wave. It's almost like they were like a cork bobbing on an ocean or on a pool. If you make a wave in the pool, the cork will bounce up and down and will feel the wave. So how will they feel it? That's the question. Well, interestingly enough, there are a couple of things that can happen. The energy of this wave, let's say there's a little electron who lives right here. And if this wave happens to hit this electron, this certain amount of energy that is associated with this wave, what if that amount of energy happens to be exactly the same amount of energy that is needed for that electron to jump up to the next level or get promoted, as we say? Well, if that's the case, when the red light hits this little electron, he will jump upwards. He will jump up to this energy level and be what we call a high energy promoted electron. Now there's a problem with this. The problem is he doesn't belong there. And there are all kinds of other rules about electron behavior that say that you can't have more than certain numbers of electrons in each energy level. And if he doesn't belong there, he has to go back. So what would happen is immediately after he felt the wave and said, woohoo, they're playing my song, and he jumped up to the next energy level, he would have to go back again and say, oh, the fun is over. And back he would go. Now, of course, to go back, he has to lose the exact same amount of energy that he got. So in order to go back, on his way back, he would make his own ripple. Remember, if you move a charged particle, that makes a ripple. If you see a cork floating in a very still pond and you move the cork, it makes ripples in the pond. So by jumping back, so I guess we could say that the initial wave caused the electron to jump up, but now he has to jump back, and in doing so, he makes a ripple. And the ripple he makes is exactly the same amount of energy as the incoming ripple, and guess what? Red light appears to be coming out of the atom. And we would see this with our eyes. And if we saw red light coming out of the atom, we would say, oh, the object is reflecting red light. So reflecting could actually mean an object is getting a ray of energy in, an electron is jumping, and then jumping back down and re-emitting that same wave back. So that's kind of a microscopic view of reflection, isn't it? Now, what if a wave of blue light, well, let's say green light, it's a little bit different. Well, we'll use blue, what the heck. So blue comes in. Now what if blue light, which is, remember, blue light is 400 nanometers, which means it has a different amount of energy associated with it. It's not exactly the right amount. It doesn't match the energy between the two levels. In that case, the electron wouldn't jump. You can't jump unless you have precisely the right amount. So then there are a couple of options. Perhaps there's another level where an electron could jump. Perhaps an electron who was maybe down up here, he might jump. Or maybe this electron could jump. But what if the blue light happens to be the wrong amount of energy for any of the electrons to jump? Well, it doesn't go nowhere. The electrons will still feel the wave, but instead of having the precise amount of energy to jump, instead, what they might do is just vibrate a little more, which causes the entire atom to vibrate a little more, which means that this, when an atom vibrates, it does give off, because remember, moving electrons make waves, but they do not make a blue wave. The vibrating might come off as a long infrared wave or heat. So the atom vibrational pattern might produce heat. So we would say that this particular atom is absorbing the blue light, but reflecting the red light, because the red light allows one of the electrons, it's just the right amount. Now, the amounts of energy that are required for electrons to move depends on a lot of things. And it depends on not just the energy levels between these electrons, but also this atom is not going to be by itself. It's going to be joined with other atoms. There'll be millions of them all together. And of course, you know that they'll be sharing electrons, covalent bonds, there'll be some ionic bonds, there'll be all kinds of things going on. And these things will all contribute to how free the electrons are to jump around inside a very large molecule. So the summary is that the electrons will reflect light if they are the right amount for them to be promoted to another energy level. Or they'll absorb light if they basically cause just a simple vibration. And the only way to know what's going to happen, of course, is to very, very carefully study all of the properties of how this atom is situated in a particular molecule and what kind of bonds are there and how free the electrons are to move and be promoted. And of course, we don't want to get into all that. We just want to understand that that's what would be happening in the background. Now, it's interesting to note that when you look at an atom like this, the electrons on the inside are what we call the lowest energy level. However, making them jump requires a lot of energy, whereas the ones on the outside will jump far more easily. So if you have electrons in the outermost orbits, when they jump from their levels, the next level up for them isn't very far. So these guys tend to produce infrared heat. When these guys jump up and down from one place to another, and when they vibrate, we get infrared. The middle atoms tend to produce a little bit more energy, and we get actually infrared and some visible light as well. Visible light from the outer ones. The inner ones, if they start jumping up and down, you get ultraviolet and higher radiation. Ultraviolet. So we don't see this happening very often. And then if the innermost electrons get transitioned or bumped up and down, we get X-rays. So you can see that for most cases, it's the outermost electrons that are doing a lot of this transitioning up and down, bumping up and down, producing visible light and heat. We very seldom see ultraviolet light emitted from atoms, or even X-rays. It would be kind of creepy if your bed at home suddenly emitted X-rays. It would require some very high energy waves to get that to happen. Okay, so that's kind of an idea of what happens when light interacts with matter. It can do a couple of things. Basically, remember that it can be reflected. Okay? And reflected is kind of another name for re-emitted. When the electrons have rolled the wave up to a higher energy level and then wiggled back down, producing a whole new wave, and that wave comes out of the atom. Or they can be absorbed and they can be turned into heat. Right? So those are the two things that can happen, reflected or absorbed. All right, let's now talk about reflection in a bigger sense. And this will be a review of what happened in grade 10. On a large scale, we see that there's a rule about how light bounces off objects. And so you drew this picture, we drew a perpendicular reference line called the normal, and we saw that a ray of light, when it bounces onto an object, will reflect in such a way, all right, that it produces these angles. We call this the incident or incoming angle, and we call this the reflected angle. Okay? The reflected angle. And the rule was that the incident angle is always equal to the reflected angle. And that was basically the law of reflection. So then we started looking at how that might be, what might happen if you reflected off of a smooth surface or if you reflected off of a surface that was kind of rough. Well, imagine several rays of light coming in at one time. On a smooth surface, they would all follow the rule, and they would produce a very, very nice picture. All the rays of light, look at the incident light and how it's set up, and look at the reflected light. It follows the same pattern. The arrows are the same amount apart. Everything's sort of in the same place. This would indicate that if you had a picture here, image of person, then all the light would hit the reflective surface and would bounce off. And if you put a screen here to catch that incident light, you could see the image of the person on the screen quite clearly. So smooth surfaces produce clear images, like mirrors. or the smooth surface of a pond that isn't wavy, or a glass sometimes, or even a smooth, shiny metal. But rough surfaces are a little bit different. They follow the same rule. If a ray of light comes in here and hits this surface, well, it has to bounce off the surface with the same angle that it came in, which means we would have to kind of construct a little normal here and measure this, and it would kind of reflect this way. Follows the same rule. But another ray of light right beside it, I'll change colors just so we can see it, would hit here. And we would have to construct a little normal here, and it would kind of bounce this way. And then another ray of light sort of beside that one would strike here, and it would almost bounce straight back on itself. And so you see what's happening. On the rough, diffused surface, light is reflected. But it's the relationship of where the light was when it started coming in is all messed up. It's not preserved. So you would, if you had an image here, or a picture of a person, light was bouncing off the person and was hitting this rough surface. While there might be some reflection of light, nowhere are you going to be able to put a screen and collect an image of a person, because the bits and pieces of the person are kind of scattered all over the place. So there's really no way to get a clear image. So we see that smooth surfaces produce clear images, and rough surfaces produce a diffuse. We call this a diffuse image. It's not an image at all, in fact. If you put a screen there, you might capture some light, but it would be blurry light that doesn't form a nice picture. And then you went on and talked about how light reflects off of mirrors, right? And you talked about plane mirrors, and you talked about curving mirrors. But really, it's all just using the same principle. If you have a person, let's put a little arrow here, or let's put a little person here, with just the head and the body. And of course we said, well, let's imagine a ray of light that shines off here and hits the mirror. Well, it's going to bounce off with exactly the same angle. What's cool is that your eyes and your brain don't really understand that light is bent. When they see light coming in, they just assume it came in a straight line from wherever it's coming from. So if your eye saw this ray of light right here, there's your eyeball, it would imagine that this ray of light must have come from somewhere way back here. It wouldn't be able to tell that it has bounced. Now, we take another ray of light from the very same spot, so it carries the same information, right? It's the same piece of sort of light. We bring it down here, and it comes in this way. Well, we draw our normal line, and we see that it would reflect like that. But again, an eyeball that saw this reflected ray would not be able to tell that it was bent by the mirror, and it would think that the light must have come in a straight line from somewhere back here. If I were to keep doing this with any possible ray, let's do one more just to show you. I'll have this one kind of go here, like that. Well, make a little normal, it would bounce like that. Now, of course, this is where it gets tricky when you're not using a ruler and you're just guessing like I am. You have to kind of imagine it. It would sort of bounce like that, and if you looked backwards at where it looks like it's coming from, it would come from there. You can see the pattern. Every single piece of light that bounces off the tip of this head and hits the mirror anywhere is going to appear to have come from this particular spot right here, which means inside the mirror, that's where you'll get an image of the tip of the head. And if you do the same procedure for all the spots all along here, you'll find that you'll get a nice picture over here that's very symmetrical. And that's why we look in the mirror and see images that look like they're inside the mirror in what I like to call mirror land. So that was grade 10. Then you went on and you said, okay, well, what if you curve the mirror? Well, in a curved mirror, you notice that a ray of light that's coming in follows the same rule. It has to bounce out at the exact same angle. So you'd have to create a little normal, and you'd have to bounce it down like that. And then another ray of light over here would come in, and you'd create a little normal at that point, perpendicular, and it would bounce sort of like that. And then another ray up here would come in, and you'd make a little normal, and it would bounce like that. And you start to realize that all the rays coming in this way are all going to bounce in such a way that they bounce through this little spot in the middle. And so we call that the focus. It's the focal point of where all the light rays that come in will hit, all the parallel light rays. So we talked about how curved mirrors have a focus, and then you went through a lengthy procedure of how to figure out if you drew an axis, right, and how to figure out where the images would be. And the cool thing about curved mirrors is you have lots of options. They're not as simple as a plane mirror that has one option. And there were some rules, you learned different rules, like a ray that's parallel to the principal axis will always reflect through the focus, and a ray that reflects off of the vertex will reflect as if it was reflecting in a plane mirror, and you learn that a ray that reflects through that shines through the focus will reflect parallel to the principal axis, and so on. Those were shortcuts to having to figure out these. You didn't have to draw these little normal lines and measure with your protractor. You could use those shortcut rules to produce all the different images that you got in mirrors. All right? And so that's how mirrors worked. And that was reflection, basically. And I'm sure if you went back to your grade 10 notes, you could get all that back. But what we really want to focus on is this idea of light waves actually being waves and carrying energy that causes electrons to jump from one orbit to another, or causes the atom to vibrate and become warmer. All right? And that's really the whole idea between the interaction of light waves and atoms. Now, we should mention, we were using examples of red light and blue light. I can use this picture, I suppose. What if I erase some of this, just so that we can work on this picture a little bit more. Let me erase this guy too. We don't really need that. I want you to imagine what might happen if you used a high energy ultraviolet light. Well, ultraviolet light is high enough energy that it might hit one of these electrons, say this guy. And instead of bumping him up to the next level where he's going to go back down and produce a ripple, it's going to knock this guy clean off of the atom. This is called ionizing radiation. And if you knock an electron completely off of the atom, you really upset things a lot, because now you've changed the overall charge of the atom. And that could have some serious consequences to the molecule that this atom was bonded to or was built in. And so ultraviolet light can disturb atoms to the point where it breaks them. It knocks pieces off of the atom. And the same is true for things like X-rays, which are very high energy, and gamma rays. And that's why these kinds of radiation, or these kinds of ripples, they're so vigorous, they can destroy or they can disrupt matter in such a way that if these atoms happen to be in your body as part of the molecules in your cells, or especially your DNA, they could cause errors and mistakes and omissions in your genes that could be interpreted by your body as all kinds of things. One of the main ones, of course, is a messing up of the instructions regarding cell growth, which causes cells to grow uncontrollably and develop tumors and cancers in your body, which is why we say that ultraviolet light can cause skin cancer. Okay, now, what if you had Yes FM, a very low, Yes FM right now, right, radio waves are coursing through your body as well. How come the radio waves aren't doing anything? Why aren't they causing your body to be responsive in any way? Radio waves do not have enough energy to make very many electrons move. Not in the kinds of molecules that we have in our body anyway. So we think that when radio waves pass through our body, the waves are like big, giant, rolling ocean waves, and the atoms are virtually unaffected. The electrons don't move much, and not much happens. Now, there are all kinds of studies going on to see if there might be some other hidden effects that radio waves might have on biological molecules and cells, but the jury is still out on whether that will show any real major effects. As far as we can tell right now, you can have all the Yes FM flying through your body that you want, and it doesn't seem to have any effect on your cells and on your health. Now, microwaves are a different story. Microwaves, let's erase this one. Microwaves are slightly more energy, but they're not that much. Visible light, believe it or not, has more energy than microwaves because they are shorter wavelengths. Microwaves are not very high energy, but there's a very special thing about microwaves and water molecules. Water molecules happen to be in such a way that remember how we said everything has kind of a resonant frequency with sound? Everything likes to vibrate at a particular frequency. Well, microwaves happen to be just the right song to cause water molecules to vibrate vigorously. When they feel these ripples, they get into it and they dance. Water molecules specifically. So we've learned that if we pump water or microwaves into anything that has moisture in it, the water molecules will vibrate vigorously and become very hot. And hot water can cook things and boil things. So we use the microwave to cook food by causing the water molecules in the food to dance. We play their specific resonant song. However, biological molecules inside your body would also be affected by this. There's lots of water in your body. And so if the water in your body got excited by microwaves going through your body, then they would start to cook you. So we don't want to be cooked. And this has led to the problem of the cell phone, because cell phones actually use microwaves. And so when you have a cell phone next to your head, it's putting microwaves all into the space all around it, including your skull. And so researchers were concerned, well, what about these microwaves going into your skull from your cell phone? Are they cooking your brain? And here's what we've sort of come up with so far. The amount of power in a microwave is not the same as the amount of energy, right? The amount of energy is like how much money you have. Power is more like how quickly you spend your money. Okay, sorry about that. We had a fire drill right in the middle of the recording. But we're talking about cell phones and the microwaves that are coming out of cell phones and whether or not they might have an effect on your skull when they cook you. And I said that it has to do with the level of power, how fast the waves are transmitting the energy that they're transmitting. So what turns out is microwaves from your phone have a very low power level, whereas the microwaves in your microwave oven are much higher. They transmit their energy at a much faster rate, which means that you will get far more damage from the microwave oven than you would from your phone. Some scientists have concluded that microwaves from your phone are not powerful enough to cause any significant damage, whereas other scientists have said that even though the power is low, you can get significant damage if you are exposed to this low power for a very long period of time. So the jury is kind of still out about whether cell phones affect your tissues. And there are some very interesting studies that show that there are actual correlations between cell phone use and tumors in the brain and so on. So this is not a done deal. We cannot say for certain whether cell phones and other electronic devices are doing any damage to our bodies. All we can say is that it doesn't appear to be damage that's easily observable, and it might take a very long time for that damage to show up. But other than that, we use them safely, minimize our use hands-free devices and so on. We are in no more danger from cell phones than we are from every other electronic device that we have. And I think we'll call it quits there. You can hear the bell ringing in the background. That is a review of reflection and how light interacts with matter.